undetermined coefficients to solve non-homogeneous equations, right? So it allowed us to find the particular solution, but the method was limited to a small subset of functions. So those were polynomials, exponentials, sines and cosines, and their products, right? So if the forcing function, the function that makes the equation non-homogeneous, is more complicated, so by more complicated it means that as you take more and more derivatives, you get more and more functions like log x. Remember, it never started to repeat itself, then that method would fail. So this method is called variation of parameters. And it will allow us to find particular solutions for equations that have more complicated functions. So
Dang it, I wanted to throw it on the floor first.
so the foundational assumption is a lot like that of the one for reduction of order. Do you remember the assumption that motivates reduction of order? That's the one where you substitute.
W u prime.
Yeah, you reduce the order w equals u prime. But
Y2 equals u y1.
right, so y2 equals u y1, where u is non-constant. Right, so the assumption's very similar to that for variation of parameters. So if you have a homogeneous equation, so we're only going to discuss equations that are order 2. The method can be generalized for higher order equations, but it's significantly more complicated. So we will restrict the discussion to order 2 equations. So if you have a homogeneous equation, if it's order 2, then the general solution looks like what? Well, it's y equals some constant times one solution plus some constant times a second solution. These two solutions are linearly independent, right? So you have these two parameters which are constant, right? So the assumption is, well, if you have a non-homogeneous equation, then perhaps the general solution looks like this. Where the parameters are non-constant, so variable. So that's where the method gets its name. So variation of parameters. So the assumption is that the parameters multiplied by the solutions to the homogeneous equation are non-constant, so that they're variable. So for this method, rather than going through the method each time, we're going to appeal to a formula. If you're interested in the derivation of the formula, you can read about it in the textbook, but in order to solve the resulting system, the author uses Cramer's rule. I don't know if any of you are familiar with that. You might have seen it once or twice in other places, but basically it uses determinants in order to find solutions to a system of equations. So you'll probably never see it again, and it's not a rule that most people are familiar with. So we will work with formulas that give us these parameters. Okay, so if you have an equation in standard form, so this is the equation in standard form. Call y1 and y2 solutions, linearly independent solutions. Associated homogeneous equation. So remember Wronskian of y1 cross product.
So maybe even non-B0 or something.
It's a determinant. It's a determinant of this matrix. So y1, y2, and their derivatives. Okay, so given all of this, we have two formulas for the derivatives of these parameters. So u1 is equal to minus f of x y2 over the Wronskian of y1 and y2, so u1 prime, and then u2 prime is very similar. Let's see if I got this right. Okay. Right, so these are very similar to each other. The only difference is this one has a negative sign, this one's positive, right? So the subscripts are alternate. The reason for this negative sign is if you interchange the meaning of y1 and y2, that would interchange these columns. If you think about the formula for the determinant, that's going to switch the sign. So that's why the two formulas differ in sign. Okay, so I'd like you to memorize these two formulas.
Is,
Yep.
is that
Is what?
just down here, this matrix?
This Wronskian, yeah. So what do you need to know to use the formulas? You need to solve the associated homogeneous equation. That gives you y1 and y2. Make sure that you put the equation in standard form, so if this coefficient isn't 1, divide by it. And then once you solve the associated homogeneous equation, you can find the Wronskian. Okay? So these give you formulas for the derivatives. You integrate them, and then you substitute into this. Okay, so it's pretty, yes?
So this is kind of a stupid question, but can you refresh me? How do we know, like, if Q of X and F of X are flipped? Like, because that would change it, or does it?
Oh,
not
I'm
matter
sorry.
if it's gonna change
This
it?
should have, this is multiplied by y.
Oh, okay.
Okay. Yeah, that's a good point. Okay, so I guess you could use this method even if it were a simple function, like polynomial, exponential, sine or cosine. It's not too difficult to use the formula. Sometimes the integration can get a bit difficult, so I would say, generally speaking, it's easier to solve the system of equations when you're using the method of undetermined coefficients than it is to use these formulas. Okay, so let me show you how this works with the first example. Okay, so this is a linear equation with non-constant coefficients. I'll show you how to solve this in the next section, or at least solve the associated homogeneous equation in the next section, but since we don't know how to do that yet, let me give you y1 and y2. Okay, so given that y sub c, so the solution to the associated homogeneous equation, c1 x plus c2 x minus 1. All right. What does this tell us?
Get a standard form first, right?
So we can do that. Okay, so this is f of x. What do we need?
We need a y1, y2.
Yeah, we need f of x, y1, y2. What are y1 and y2?
Integrating factor, right, solve
separating factor is used for first order linear equations.
Y1 is X,
Yeah.
Y2 is X.
So this is Y1, this is Y2, or if you want, you can switch. Right, so you need the two linearly independent solutions of the associated homogeneous equation. Right, those are the solutions that form the complementary function. Y1 is X, Y2 is X minus 1. Okay, so we can use these two to find the Wronskian. Okay, so derivative is 1, this derivative is minus x minus 2. Okay, so the determinant is this multiplied by this. Subtract this multiplied by this. Okay, so these are the four things that we need to use the formulas. Okay, so minus f of x multiplied by y2, so we're calling y2 x to the minus 1, divided by the Wronskian, minus 2x to the minus 1. Okay, so if we simplify this, this is positive, these cancel, minus x to the minus 3x. Okay, so to find u1 we integrate. So u1 is equal to what? So plus 1 is minus 1/2 divided, so it's negative 2x to the minus 1/2 plus c1. Question? Better?
Thank you.
Okay. So this is U1, U2 is f of x, y1 over w, that's x minus 3 times y1 is x divided by w. Alright, so this is x squared times this x to the 1/2, so negative 1/2 x to the 1/2. Right, so 2 is equal to, so it's 3/2, so divided by 3/2 is 2/3 times this, negative 1/3 x to the 3/2 plus c2. Okay, so what does all of this mean?
We find a particular solution.
It's actually going to give us the general solution. And so if you introduce these constants, this will give us the general solution. Right, so the foundational assumption is that the general solution is u1 times y1 plus u2 times y2. Okay, so u1 is this times y1 is x. U2 is this Okay, so this is supposed to be the general solution. What is the complementary function? Right, this is supposed to be, this should be YC plus YP. So of these three terms, which are part of the complementary function, which are part of the particular solution?
C1, C2.
C1, C2 is YC, and then this is the particular solution. Right? So it's not necessary, but let's check to see if this actually works. So if this is the particular solution, then what?
Get 0, okay? No.
You'll get 0 if you substitute the complementary function.
Okay.
How would we check if this is the particular solution?
Do derivatives and substitute.
Substitute, it should satisfy the equation itself, right? So the equation is, so let's take first and second.
Okay, so first derivative, so half, so it's minus 2/3 x to the minus 1/2. Second derivative, 1/3 x to the minus 3/2. Okay, so if we substitute x squared times 1/3 x to the minus 3/2 plus x times minus 2/3 x to the minus 1/2 minus 4/3 x to the 1/2. This should all be equal to x to the 1/2. Right? So this is 1/3 x to the 1/2 minus 2/3 x to the 1/2 plus 4/3 x to the 1/2. So 1/3 minus 2/3 minus 1/3 plus 4/3 is 3/3, so x to the 1/2 equals x to the 1/2. Pretty simple. No.
Not at all.
No.
Sounds like a
What?
lot of work with an analog. Just, I think, on that over there, it's C1X.